Hello, my name is Christian Gobert, and I'm a PhD student at Carnegie Mellon University, and this is going to be a research presentation on quantifying spatter. Uh, so here we have our presentation introduction. Other contributors to this work include a fellow PhD student, Evan Dywald, and my advisor, Professor Jack Booth. So spatter in the laser powder bed fusion process is the ejected material from the melt pool region due to that laser material interaction. So if you take a high-speed camera and you point at the melt pool process, you'll see those spatter particles being ejected from the melt pool. Here on the right, we have, if you take a picture of your powder bed, you can see the spatter landing back on the bed, causing disruptions from the printed material. And then in some previous research by Gasper and al., they showed a stark difference between virgin powders and recovered spatter particles, mainly in the size and the shape of those particles. And then the possibility of a defect could be caused by a spatter agglomerate landing back on the build substrate. And now you have a mismatch between the apparent layer thickness and your melt pool size, leading to lack of fusion, induced porosity. And so our high-speed camera we're using here is a Photron AX200, and it's mounted on CMU's EOS M290 laser powder bed fusion system on the top viewport. And the challenges with this setup is that we rely on the use of incandescent light to view the scene. That is to say, we only see the hottest material. We also have to deal with a coupling of frame rate, integration time, also known as shutter speed, and field of view. And lastly, we do produce a large volume of data when doing high frame rate recordings. So with our camera settings here, we can select either a high frame rate setting, which makes it easier to track motion, but we have a smaller field of view and less light to view the scene. Or we can do a low frame rate setting, which we get a larger field of view. We have more light, but it's harder to track motion of the particles. And what we found works best for us for tracking and identifying spatter particles is a 22.5 thousand FPS with a 512 by 512 pixel resolution, which covers an area roughly 4.5 by 4.5 millimeters square. So here is just showing a back and forth rastering of a melt pool with spatter ejections shown. So to understand the temperatures we're seeing in our high-speed videos, what we've done is we've correlated lengths of image intensity contours to those of temperature contours you'd get for the Rosenthal solution for a moving point heat source. So that red outline there is the maximum image intensity threshold. So that's the approximate melt pool shape. And then this green contour here is a 20% image intensity contour. And we'll use this later on to distinguish to be a threshold for spatter particles. But what we've done is we've aligned the lengths of that image intensity contour, the green one, to temperatures you get in the Rosenthal solution. And depending on your material properties, where absorptivities for what we're using Ti-6-4 in these experiments can range from 0.35 to 0.45. That green outline is approximately 1100 to 1400 degrees Celsius. And that's a pretty substantial temperature relative to the Ti-6-4 melting temperature of 1650 degrees Celsius. So what we'll be doing is detecting spatters above that temperature threshold, essentially. So here's our process pipeline for identifying and tracking spatter particles with machine learning tools. So first, we take a high-speed image frame at time t. We process that through a segnet, and that produces a segmentation map at time t. Now we do this all for all the images in our data sets. Once we've gotten all the segmentation maps, we then move to using our TrackNet. And now that predicts the pairwise similarities between the n number of spatter particles in time t with the m number of spatter particles in time t plus 1. And now that gives us a similarity matrix of the similarity values, and then we use an assignment scheme, and we use that to do the pairwise tracking so that we get the bounding box assignments across the image frames at t through, let's say, t plus 4 of the bounding boxes to track those individual spatter particles. So first, we'll just show you the segnet, and that's where that is in the process pipeline. And segnet is a UNet-like architecture which classifies each pixel in our high-speed image frames as either the background, spatter, or melt pool. Spatter particles here are identified as having a minimum image intensity of 20% in accordance with that Rosenthal approximation to temperature we showed earlier. We also had the stipulation that any particle must have a minimum equivalent diameter of 5 pixels, so roughly 45 micron diameter. Next, we show, or next here, we have the melt pool, and that's the region of maximum image intensity pixels surrounding the laser material interaction zone. That is that red image intensity contour we showed earlier as well. And then lastly, anything that's not a melt pool or spatter is denoted as a background. And so on the bottom left here, we show the architecture for the SegNet model. So given an image input, which is the current image frame to process, as well as the previous 3 and subsequent 3 images to in the high-speed image videos movie. We process that, and then that outputs a segmentation map. We process this at the native 512 by 512 resolution, and the unit has processing of the images at multiple scales to enable the convolutional layers to have a larger receptive field. And on the right here, we just show an instance of a high-speed image frame with a melt pool, some spatter particles, cooling substrate, and the accompanying prediction from a trained SegNet model that identifies the melt pool with the red, spatter, and blue, and the background in green. So here we're just talking about the training and testing of SegNet, and we did this through 4-fold cross-validation. And in 4-fold cross-validation, we divide our data set into 4 subsets. We use 1 for testing, the rest for training, and we cycle through all possible combinations of training and test data. In addition to this, we also train a final network, and that is used to process our later data sets for analyzing spatter generation. And our data set here is 6,000 hand-labeled images for spatter and melt pools objects. During training, we include data augmentation, such as random rotations and XY flips. We train this on an NVIDIA 2080 Ti with the training time roughly 3 hours, and we use standard atom optimization hyperparameters. On the bottom left here, we show the validation loss during training as a function of training epochs, and we show the convergence of all the networks to similar loss values in a similar period of time, indicating network generalization. And then lastly, we show test classification metrics for spatter particle detection. So this we're showing the recall and precision of detecting spatter particles. Now, recall denotes the percentage of spatter particles that were labeled as spatter that were detected accurately by SegNet, where precision denotes the percentage of spatter particles predicted by SegNet that are actually spatter particles. And the final results here is that our final network, which we use to classify the later data sets, is a 94.8% recall and a 92.6% precision. Next, we'll talk about TrackNet, and that's where this falls in our processing pipeline. So this takes in the segmentation maps, and then we'll produce our similarity values we need. So TrackNet is used to predict the similarity of value between 0 and 1 between any 2 particles across any 2 sequential frames. So input to the network is the current and next optical image frame, as well as the segmentation maps from SegNet of only the particles that we want to track. And so an instance of what is input here is shown on the right. So we have our images at time t and t+1. And let's say we want to track that particle in the blue bounding boxes. Well, we just provide it as well with the segmentation maps of just those particles from SegNet. So the blue bounding boxes here are just for visualization, and they're not included in the TrackNet predictions. Here we just show the CNN architecture, so downsampling from a reduced resolution. So we actually don't process these at the native 512 by 512, but actually we downsample those to 128 by 128 beforehand, and then we output a value of 0 to 1 for the similarity, and 0 being not tracked, 1 being tracked. And then to get the similarity matrix, what we do is we process the TrackNet. We use the predictions for TrackNet n times m times, where n is the number of particles in the first image frame and m is the number of particles in the second. And then those values are placed in a similarity matrix, which contains the row and index similarity values of the nth and mth particles. So here we just showed the training and testing. Again, we're using 4-fold cross-validation to assess the performance, and then we additionally train a final network that is used to process the later data sets to analyze spatter. Our data set here is 30,000 tracked image pairs and non-tracked image pairs. Similar data augmentation is used, training on a NVIDIA 28 Ti again. Training time is about 3 hours. We're using standard atom optimization, and we show the validation loss during training, again, plateauing to similar values, indicating network generalization. And then last year, we show our test classification metrics. Again, we have recall for the track particles is 98%. So of all the tracked particles in our data set, we've detected 98% of those accurately. And precision here is 93%. So of all the tracked particles we predicted as tracked, 93% of them were actually tracked particles. Lastly, here we talk about how we take our similarity values from our TrackNet and we actually use those to align the bounding boxes to where we need them to be in our high-speed image frames. So essentially this is an assignment problem. And to begin with, no two particles can be connected if their similarity value is below 0.5. And a particle can only be assigned to one other particle in the next image frame. And we begin the assignments by proceeding in descending order of similarities. So we first start with the highest similarity. So given, let's say, 2 image frames at time t and t+1, and let's say we have these 3 objects in each, we use TrackNet to do the pairwise similarities of all possible combinations. So that'd be 3 times 3, so 9. We start with the highest similarities first, and that's the green particle, so 0.95 similarity. That assigns those objects to each other, and then that precludes the green objects from connecting to the yellow or the red objects. And then we just proceed through the similarities until all the pairwise trackings are made. Now, if an object does not get tracked to if a spatter object does not get tracked to a particle in the previous frame, then it is registered as a newly generated particle. And so this process is repeated for all consecutive pairs of high-speed images that contain spatter particles in a data set. And we show this implementation here for a process video. So here we're showing the rastering and printing of a laser here. So we're showing the back and forth motion of a melt pool, and we're tracking each spatter particle with a unique ID color and bounding box. So that's the implementation of the processing pipeline we just went through. Now, after that's done, we can save this information in a database. So let's say we want to go back and check where our melt pool was in that video. We have that information shown here on the right. And then what we can do later on or further on is show, let's say we can pick a scan line and we can show all the spatter particles that emerge from that scan line. And then we can also get the trackings of those particles, those spatter particles, their trajectories with respect to the scan line, the video, or the melt pool motion, for instance. So processing these high-speed information lets us examine many characteristics of spatter generation when changing process parameters, for instance. And this video took approximately 15 minutes to process with our processing pipeline. So here we're just going over some of the experiments we've done to use our developed machine learning tools. So here we're building a 3.5 millimeter geometry inside our camera's field of view. And every five build layers, which are 30 microns thick, we change the process conditions. So here we're varying either laser power, laser speed, or scan strategy. So for laser power, we're varying the laser power from 165 to 340 watts. Or we vary the laser speed anywhere from 400 to 1600 millimeters per second. And then for scan strategy, we're looking at bidirectional, stripe, and chess. So these process conditions are only showing the process variables that we changed, and those are deviated from the EOS recommended settings to produce Ti64, which is the material we're printing with. And that includes laser power of 280, laser speed of 1200 millimeters per second, bidirectional scan strategy, and 140 micron hatch, 140 micron hatch spacing. So here's our power experiments here. So we're varying the laser power for printing that 3.5 millimeter diameter cylinder. These are the process parameters that were constant down here, and then we have our variation in laser power. And on the y-axis here, we have our spatter counted at each change in laser power. Now we're showing 2 values for each video. We have an upper bound, which is the spatter total, which was identified in our videos, but we also divide that by our recall and TrackNet, our SegNet and TrackNet recalls. Now this lets us includes the inaccuracies that accompanied our machine learning tools to include that. And then also the lower bound here is just the spatter total multiplied by the segnet precision and the track net precision. So what we're seeing here is at lower powers, we have increased spatter generation. And once we're above, let's say 240 watts, the spatter generation is relatively plateaued. There's not much difference. And if we look at these laser powers in the process map of Ti-64, so you have your keyhole region here, your fully dense and your lack of fusion region here as a function of laser power on the y-axis and laser velocity on the x-axis. You can see that our lower powers are just about in that lack of fusion regime, and that looks like it's sort of correlating with our increased spatter generation. It's very interesting to see, and that we're able to extract that with our processing pipeline, that might line up there. So next we look at our spatter ejection times of the laser power experiments. So here we're plotting these distribution of ejection times in cumulative distribution plots. Now in cumulative distribution plots, this plots the probability on the y-axis that any value will fall below that on the x-axis. If the distribution is uniform, the slope at each point of the x-axis would be equal, where the larger the slope of the plot at any point on the x-axis, the higher the probability of that point occurring. So for these cumulative distribution plots, as the laser power increases from 165 to 340 watts, the slope of the distribution significantly increases at or before the 10th frame in the scan line. And that is to say that at higher powers, spatter ejection times tend towards the beginning of the scan. So very interesting to see there as well. Next here, we're looking at our speed experiments here. So on the x-axis, we're varying the laser speed. We have our constant process variables as well. On the bottom there, asterisks. We're showing the upper and lower bounds for each experiment, and with spatter counted on the y-axis. We're seeing a large number of spatter generated as relative to the higher velocities here. And if we look at where those process parameters lie in the process map we showed earlier, with the keyholing, fully dense, and lack of fusion regime, we can see that our lower velocities are in the keyholing regime. And it looks as though when you're in keyholing, your spatter generation is significantly increased. I mean, we're talking an order of magnitude higher here than when you're outside of keyholing. And we can also look at spatter ejection angles relative to the forward melt pool motion. So on the left here, we show how we measure this angle of ejections, and that is positive 0 to 180 counterclockwise from the moving front, and that constitutes the advancing side of the melt pool scan strategy. We also measure the angle as negative from 0 to 180 clockwise on the retreating side of the scan strategy. And so again, we're plotting these distributions in cumulative distribution plots. And one of the things we can extract from this distribution plot is that when you're in the keyholing regime or the approximate keyholing, your distribution is more uniform. So that is to say that the ejection angles are not influenced by the melt pool motion. Whereas for the higher laser speeds that are outside that keyholing regime, the distribution is more skewed to the rear of the melt pool as well as the retreating side of the melt pool. So to get an understanding of what a distribution line here represents in terms of where the spatter particles are going with respect to the melt pool, we can plot those trajectories. So here on the top, we're showing the captured trajectories of all the spatter injected at the 1600 millimeters per second laser speed. So that is this cumulative distribution plot up here. And that's what that looks like. Now, if you're to look at the severe keyholing, so 400 millimeters per second, that is a more uniform looking cumulative distribution plot. That's what all those spatter ejection angles look like. So it's going in all directions. Lastly, we look at spatter generation related to scan strategy here. So we have the bidirectional, stripe, and the chess. We also do the stripe and chess at 2 millimeter and 1 millimeter thicknesses. So we show that when we switch from bidirectional, stripe, or chess, spatter generation is increased, as well as when we decrease the stripe and chess widths from 2 to 1 millimeters, both of those cases, that spatter generation is further increased. So as we decrease the length of the scan lines, we're seeing significant increases in spatter generation. So last, just to conclude, we've demonstrated the ability to track spatter trajectories with machine learning tools. We showed that processing pipeline. We went through the validation and showed the performance of that. And then we were able to analyze a multitude of high-speed videos to gain some physical insights into spatter generation. And what we showed is how laser power can impact how quickly spatter begins after a scan start. We also showed how spatter has a preference to eject towards the rear of a melt pool, but then that preference changes as we switch to keyholing, which then starts to eject spatter particles in all directions. And lastly, we showed how scan strategy can have a drastic impact on spatter generation. And I'd like to end by just showing two instances of spatter particles ejecting from the melt pool. So on the top and bottom here. On the top here, we're showing the spatter ejection landing back on the build substrate in front of the melt pool. And on the bottom here, we're showing spatter ejection landing back onto the previously melted regions. And I'd like to end by thanking you all for your time.